Hello friends, in the previous lecture we have seen that what is meant by equivalence relation, and we have to take some example on that equivalence relation. Today I am going to take one more example for equivalence relation and also example for power set. Okay, let us start. Write down question. First question, let capital A equal to small a comma b comma c comma small d. That is a b c d. Let capital A contain 4 elements. Then how many elements? Then write power set of A. Then write power set of A and how many elements in power set of A and how many elements in power set of A. Also find how many relations on set capital A. Question. What is your question? We have given set capital A equal to A, B, C, D containing 4 elements. Then we have to write down its power set and also how many elements in that power set, and also find how many relations on set A. Okay. So let us write down solution. This is your practice of solving the question. Already in previous lecture we have studied how to write down power set and how many relations on that set how to find. Okay. So write down solution. Let capital A equal to small a, small b, small c and small d. Okay. Then cardinality of A equal to, what is cardinality? Number of elements in that set A. So how many elements in that set A? That is 4 elements, right? So cardinality of A equal to 4. Okay. So we know that therefore cardinality of power set of A become. What is your cardinality of power set of A? In the previous lecture we have seen that if cardinality of set A is n, then cardinality of its power set become 2 raised to n. So here n become 4. So cardinality of power set of A become 2 raised to 4. So this value, that is 16. So how many elements in that power set of A? That is 16 elements. And power set A become, so what is your power set A become? Okay. So I am going to write down this power set A. Okay. So first element become empty set is always subset of any set. Okay. So next element is singleton A, next element is singleton B, next is singleton C, and last is singleton D. Okay. This is for singleton element. Next element is set containing 2 elements, that is AB, next one is BC, okay, next one is C comma D, okay, next one is A comma C, next one is A comma D, okay, now also BC containing, CD containing, next containing B comma D, okay, and C comma D also complete, okay. This is for set containing 2 elements. Now set containing 3 elements. So therefore set containing 3 elements is A comma B comma C, okay. Next A comma B comma D, okay. Next is D comma C comma D, right. Next ABD, next ACD also, right. That is A comma C comma D also, right. Then is BCD, ACD also complete, okay. ACD, and your last is, that is A comma B comma C comma D, that is your whole set. Now we have to check that it is 16 elements. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So all elements are complete here. So this is your power set of A. Okay. So what is your next question? You have to also find how many relations on set A. Okay. So relation become, so number of relations on set A become, that is number of subset of A cross A. Okay. So first we have to find how many elements in the set A cross A. Okay. Therefore, set A cross A contains how many elements in set A? Set contains 4 elements. Therefore, set A cross A contains 4 cross 4 elements. Therefore, set A cross A contains 4 cross 4, that is 16 elements, right? How many elements in that set A? It is 16 elements, and number of relations become on set A become, that is any subset of set A cross A. So set A cross A contains how many subsets? And A cross A has 2 raised to 16 subsets, right? A cross A has how many subsets? There is 2 raised to 16 subsets, right? Therefore, number of relations on set capital A. Number of relations on set capital A is how many relations on set A? That is number of subset of A cross A. So how many subsets? That is 2 raised to 16 subsets. So how many relations on set A? That is 2 raised to 16 relations on set A. Okay. This is so simple question. So next question I am going to write. That question depends on equivalence relation. Okay. So that was the second question. And second question. Question 2. Let this script Z be the set of integer. Okay. Define a relation R. On Z. Define a relation R on set of integer by let A comma B be integers. We have to define a relation that is A equivalence B. If when is A equivalence to B? If A minus B is an even integer, right? A minus B is an even integer. Okay? Then show that equivalence. Then show that this equivalence is an equivalence relation on set of integer. So what is your relation? Let Z be the set of integers. We have to define a relation R on set Z is how to define this relation? A equivalence with B. If when this A equivalence B, if A minus B is an even integer, then this R is a relation on that Z. Then we have to show that this equivalence is an equivalence relation on set of integer. Okay. So now solution. We have to show that this equivalence relation. Then we have to show that it satisfies 3 properties. That is first reflexive, second symmetric, and last one is transitive. Okay. So that is the first one. That is the reflexive properties, right? Okay. So let small a be any integer, right? Such that A minus A equal to, such that A equivalence with B. A equivalence with B if A minus B is an integer. Okay. So we have to first property for reflexive. That means A equivalence with A. And we have to check that A minus A is even integer. Okay. So let A is an integer such that A minus A become 0. right? A minus A become 0, and 0 is an even integer, right? 0 is an even integer, okay? So this 0 is an even integer, that means A minus A is an even integer, therefore A equivalence with A, right? Therefore equivalence is reflexive relation, right? This equivalence is a reflexive relation. This is your first property, right? So second property, what is your second property? That is symmetry. Your second property is symmetric property. What is your symmetric property? Let A comma B be into integer, right? Such that A equivalence with B. Such that A equivalence with B. Now A equivalence B with B means A minus B is an even integer, right? A minus B is an even integer. Okay. Now we know that if A minus B is even integer, therefore minus of A minus B is also even integer, right? Is also even integer. Why this happen? Just 2 is even integer, then minus B is also even integer, same 8 also even integer, then minus 8 also even integer, right? So using this one, A minus B is even integer, then minus of A minus B also even integer, right? Take minus side inside, then what will you get? So minus of A minus B become B minus A is also even integer, right? B minus A is also even integer, right? So what do we get? B minus A is also even integer. That implies B minus A even integer means B equivalence with A, right? So what do we get? We have to assume A equivalence with B. So we get B equivalence with A. So what do we get? So this equivalence is an symmetric relation. This equivalence is an symmetric relation, right? This is your second case. What is the last third one? You have to check that this equivalence is transitive relation, right? Third property is transitive relation, right? So what is your transitive relation? Let small a comma small b comma small c are integers such that A equivalence with B, right? A equivalence with B means A minus B is even integer, right? A minus B is even integer. Also B equivalence with C, that implies B equivalence with C means by doing this equivalence relation, B minus C is also even integer, right? B minus C is even integer. And we have to show that in that transitive property, if A equivalence with B and B equivalence with C, then we have to show that this A equivalence with C. So for that we have to consider A minus C equal to. So we have to consider A minus C equal to. If A minus C is even integer, then A equivalence with C, the transitive property hold. Okay. So we have to consider A minus C equal to. So I am going to write this A minus C become A minus B plus B minus C. Okay. So A minus C I am going to write this one. I am adding plus and minus here, B here. Okay. Plus and minus B here, then we get. So this A minus B plus with B minus C. So we will get this A minus B also even integer, also B minus C also even integer. In addition of 2 even integer I get even integer. So if you will take 2 plus 4, 2 even integer, 4 even integer, then 2 plus 4 is 6, also even integer. Therefore A minus B even integer, B minus C also even integer. In addition also even integer. Now this addition, that is A minus C is also even integer. So this is also even integer, right? So what do we get? A minus C is even integer. So A minus C is one integer, that means A equivalence with C, right? So this A minus C is one integer, that implies A is equivalence with C. So that implies equivalence is transitive relation, right? This equivalence is transitive relation, right? So what we get? So we have this given relation is reflexive relation, second one is symmetric relation, third one is transitive relation. This equivalence satisfies all these three properties. Therefore, this equivalence is an equivalence relation on set of integer. Okay, this is your example. So let us now define the definition of equivalence relation. Then I am going to find out equivalence class of that set A. Okay. So let us write down next definition. What is meant by equivalence class? What is meant by equivalence class? So write down definition. Definition of equivalence class. So what is meant by equivalence class? Okay, it is so simple definition. Let equivalence be an equivalence relation, be an equivalence relation on your set capital X. Let be equivalence and equivalence relation on set capital X, and small x belongs in capital X, small x belongs in capital X, then the set collection of all y, that is the set collection of all small y from that set capital X, such that x equivalence with y, such that x equivalence with y, where x is also member of that set capital X, is called as equivalence class. Is called as equivalence class of x on your set capital X. Okay, this is called as equivalence class of x on your set capital X. It is denoted as equivalence class is denoted as in a closed bracket x or x bar. Equivalence class is denoted as closed bracket x or x bar. Okay. So therefore, what is my equivalence class of x? So what is my equivalence class of x? That is collection of all y from that set X, such that x equivalence with y. This is your equivalence class of A. So let us take example. In the previous example, what is your previous example? Let your capital X is your set of integer. Okay. So we have to define let A comma B be your set of integer and define. So we have to define A equivalence with B. Okay. Let X is set of integer. A and B are unique to integers. We have to define an equivalence relation A equivalence with B if A minus B is an even integer. Okay. A minus B is an even integer. Okay. Then we have to find. Equivalence of class of A. Then we have to find equivalent class of A is. So what is your equivalent class of A? What do you mean by equivalent class of A? It is the collection of all y. So we can take this collection of all B from set of integer, right? It is collection of all integers B such that A equivalence with B, right? What is your equivalent class of A? collection of all integers small b such that a is equivalent with b. Now already we have given what is my a equivalent with b? A equivalent with b means a minus b is an even integer, right? So what is this one? This is a collection of all the integers b such that a equivalent with b means a minus b is even integer, right? A minus b is even integer, right? Now we know that any even integer which is of the form, any even integer is of the form 2k form, right? It is multiple of 2. And any odd integer is of the form 2k minus 1 or plus minus 1, right? Any odd integer is of the form 2k plus 1 or 2k minus 1, and any even integer is of the form 2k, that is multiple of 2. So this a minus b is even integer, that means all collection of integers get such that a minus b equal to 2k, right? And where k is integer, right? So what is the equivalent class of a? Equivalent class of a is become collection of all integers b such that a minus b equal to 2k, where k is integer. That means equivalent class of a become collection of all integers b such that a minus b equal to 2k. This minus b is shift over side there plus, then we get a equal to b plus 2k, right? Where k is integer. This is your equivalent class of a on that example. Okay? What is your equivalent class of a? Collection of all integers b such that a equal to b plus 2k, where k is again integer. This is your equivalent class of that example. Okay? So it is so simple. So today we have to study equivalent class and that example. So we have to take one more example on that equivalence relation. So take the another example of that equivalence relation. Take the example. Let x be the set of all natural number cross natural number. Okay. Let your set x be the collection of all natural number cross natural number, and a comma b being natural number. Okay. Define a relation R on X. We have defined a relation R on X as order pair A comma B equivalent with order pair C comma D. If what is your relation defined? This order pair A comma B, because your set X is n cross S, n cross n, that means in tuple form. So that is order pair form. That is order pair A comma B is equivalent with order pair C comma D. When this equivalence, if AD equal to BC, then you have to show that this equivalence is an equivalence relation. Then you have to show that this equivalence is equivalence relation on your set of natural number cross natural number, that is your set X. Okay, we have to show that this is your equivalence relation. So how to show that? And our solution. How to show that this is equivalence is your equivalence relation? That we have to show that it satisfies reflexive, symmetric, and transitive property. So the first one, that is your reflexive property, right? So what is the reflexive property? Let A comma B be your natural number, right? So we have to show that A comma B is equivalent with A comma B, okay? That means let A and B are natural number. We have to show that A comma B is equivalent with A comma B, right? That itself Okay, let A comma B be natural number and A comma B is member of n cross n. Okay, A comma B is a member of n cross n. To show that A comma B is equal to A comma B. To show that A comma B is equivalent to A comma B. So when is A equivalent to A comma B? That is to show that this is happen. Okay. Let we can write AB which is written as DA, right? We can write this AB which is written as B. That means 1 into 2 is 2 into 1. That is multiplication is commutative. Because 1 into 2 is 2 and 2 into 1 is also 2. So both are equal, right? That is 3 into 4 which is also as 4 into 3. So this matrix that is multiplication of two numbers is commutative. That is multiplication is commutative, right? Therefore n is natural number. Then we can write AB as B also, right? So by using this one, by using this relation, AD equal to BC, that means AB is equivalent with CD. So AB is equal to BA, that means A comma B is equivalent with A comma B, right? Therefore equivalence is reflexive relation, right? Equivalence is reflexive relation, right? So that is the second one. What is second relation? That is symmetric relation, right? So second relation is symmetric relation. So let A comma B belongs in natural number cross natural number, okay? And let A comma B is equivalent to C comma D. Let we have to also A comma B is equivalent to C comma D. Then now A comma B is equivalent to C comma D. That implies AD equal to BC also, right? Okay. So therefore, what is implying? We can write this AD equal to BC as that is CB equal to DA also, because this multiplication is also commutative. We can write this x if x equal to y, then y is also x. We can write this also as, right? So AD equal to BC, we can write this also as, we can write AD also as DA, and we can write BC also as CB. So AD equal to BC, we can write this as CB equal to DA also. Now using this one, what we get? That is C comma D is equivalent to A comma B. So we have to assume A comma B is equivalent to C comma D, and we get C comma D is equivalent to A comma B. By using the sequence relation, what we get? That is CB equal to DA. That is CB equal to DA is happen. So that implies C comma D is equivalent to A comma B. Therefore, this equivalence is symmetric relation, right? This equivalence is symmetric relation. What is the symmetric relation? If x is related to y, then show that y is related to x. So it happens where x is A comma B and y is C comma D. Okay, this is your for symmetric relation. Your last third one, transitive relation. So last third case is transitive relation. Your A comma B also member of n cross n, and C comma D also member of n cross n also, right? So for transitive relation, let A comma B comma C all these are natural numbers, right? Okay, and A comma B, C comma D, and E comma F all these member from n cross n, right? All these double from n cross n. For transitive relation, let we have to assume A comma B is equivalent to C comma D. Okay. For transitive relation, A comma B is equivalent to C comma D. By using equivalence, what we get? That is AD equal to BC. What we get? AD equal to BC. That means, what is AD equal to BC? That is A upon C equal to B upon D. Okay, what do we get? That is A upon, or we can write this as A upon C equal to B upon D also, or take this B multiply, shift on right and divide. A upon B equal to C upon D also. You can write this as AD equal to BC, we can write as A upon B equal to C upon D. And B is multiply, shift divide. This is D multiply, shift divide. Okay, A upon B equal to C upon D. Okay, when this happens, if A comma B is equal to C comma D. Okay, and what is the second case? C comma D is equivalent with E comma F. Okay, then what is implies? C comma D is equivalent with E comma F by using this equation. Last, that is CF equal to DE. What is the last one? CF equal to D. Okay, from using this one, what do we get? This D is multiplied with other side and divide. Then C upon D. Then C upon D equal to E upon F. So what do we get? What is the value of C upon D? Value of C upon D is E upon F. And here value of C upon D is A upon B. Okay. Therefore, from this first and second case, what we get? A upon B equal to C upon D. And what is C upon D? C upon D become E upon F. So from these three proportional, we get, from these three proportional, what we get? From these three proportions, A upon B equal to C upon D equal to E upon F. That means implies A upon B equal to E upon F. That implies three proportions are equal. That means first equal to third one also. That is A upon B equal to E upon F. Therefore, next step we can take cross multiplication. Therefore, AF equal to B. So we get AF equal to B. So that means A comma B is equivalent with E comma F. Right? What will happen? AF equal to B by using this equivalence. A comma B is equivalent with C comma D if AD equal to BC. That's last two product and middle two product both are equal. That implies AF equal to B. That means last two, that is AF, is whose product equal to middle product, that is BE product. So AD AF equal to BE, that means A comma B is equivalent to E comma F. That means transitive case is whole. That is first equivalence with second, second equivalence with third one, and last if we get first equivalence with third one, that is first equivalence with third one, that is A comma B is equivalent with E comma F, then this equivalence is a transitive, then this equivalence is a transitive relation. So from this first, second, third one, what we get? This equivalence is reflexive, symmetric and transitive relation. Therefore, from first, second and third one, this is reflexive, symmetric and transitive relation. That implies this equivalence is equivalence relation. This equivalence is equivalence relation on your set capital X. So this your example 2 here. Okay. So I hope all parts you have understood. So this is your end of your first chapter. So remaining part we will study next lecture. Thank you.